I'll get started. I want to introduce our speaker. We have Professor Jürgen Janek visiting from the University in Giessen, and he is going to be talking about solid-state batteries. He is one of the first people working on solid-state batteries that has made a pretty critical contribution. He has numerous awards, and most recently he has been named a member of the Leopoldina, which is the German National Academy of Sciences. He has over 450 papers, and today I believe he's going to be talking about the work on lithium metal solid-state batteries. But just from a personal side, much of the work in my group over the last decade has been largely inspired by Jürgen Janek's group, so it's really great to have him here. All right, without further ado, let's welcome Jürgen.
Yeah, thank you, Kelsey, and it's in fact my pleasure to be here. Thank you for inviting me and giving me the chance to present some of our work. Of course, I also enjoy very much the weather, the campus, everything. Really, it's my first time to New Jersey and to Princeton, and enjoy that very much, and also discussions with the PhD students. So let me directly jump into it. And so this is that was the headline of a weekly magazine in Germany some years ago. Who will construct the battery of the future? And the answer, there was a sentence saying, electrochemistry is the crisp bread of the sciences, hard, dry, not glamorous. Well, welcome to my life. Now, the good thing of that is that electrochemistry, and this is my deep belief, connects, of course, the electrified energy grid of the present and expanded of the future with chemistry in our materials world. Not only with batteries, but with many other technologies. So it is essential, and I deeply believe that electrochemistry is something like the semiconductor field of physics of chemistry. It's really essential to so many things. Just think of all the sensors and whatever, and even we operate electrochemically in many respects. So just to tell you a bit where I come from, so Giessen is in fact a small university town, maybe double the size of Princeton, 60 kilometers north of Frankfurt. So that's one of the greatest things of Giessen, is that you can easily come and go via the airport in Frankfurt. And we have a relatively new building here where my major group is, and I have a second affiliation in Karlsruhe, which is a special lab together with BASF Chemical Company. And so this is, anyhow, in Giessen is my major affiliation, and there we do, I would say, more fundamental work, whereas in Karlsruhe, in the lab, which is co-funded by BASF company, we do a bit more applied research towards mostly cathode materials, which is not part of today's presentation. So I would say I have a big fundamental lag and a smaller applied lag, but I enjoy very much fundamental work against the background of, I would say, relevant things and relevant technologies. So that's why I really enjoy. Okay, before I start, I have a question to you. I hope, because I think you're close to chemistry, you know that logo. I think it's the ACS logo. And do you know what it represents? Okay, indeed. The upper part is Phoenix rising out of the ashes. So that's the symbol for synthesis. Okay, what's the bottom part, except the letters? What's the bottom part? Anyone know? Any idea? It's the so-called 5-ball glass apparatus, which was developed by Justus Liebig, in fact, which is after whom our university is named today, because he worked major part of his time, of his career in Giessen. And he was really one of the pioneers in chemistry, and he invented this little glass apparatus to collect carbon dioxide and calcium hydroxide to make it calcium carbonate, and by weighing that, then getting the amount of carbon in your organic compounds. So he really, by that, accelerated analytical chemistry. And in 1848, 49, John Smith, he was the second president later of the ACS, was a student in the lab of Liebig. And at that time, all the members of the lab had this little 5-ball apparatus as a metal piece at the jacket. And when he went back, he said, okay, we need a new logo. And he thought that this little 5-ball apparatus for him was a symbol for analysis. He made it the symbol for analysis at the bottom part of the ACS logo. So whenever you see an ACS paper or whatever the logo, think of our university in my presentation. Okay, so that brings me to the subject of solid-state batteries, and I'm sure that all of you have somehow an opinion about batteries. I will have a somehow extended introduction to the subject. Then, of course, I jump into our research and will present something, hopefully giving you something. And what you see here as a picture is already how hopefully a later solid-state battery may look like, but I will come to that later. I should say that, and I think already, yeah, okay, I think I should use another pointer. As this is fading. Yeah. So part of the work on the metal electrodes, I will tell you, is in cooperation with Linda Nazar, I think, who is known to some of you here because she's in your advisory board, and Jeff Sakamoto at the University of California. So I appreciate very much the cooperation with both. So let me jump in with the question, which battery technologies are we seeing and will we see in the future? And what you see here in this typical Ragone chart, which is a chart where you see specific energy of batteries on cell level and the power, specific power. Let's concentrate on the amount of energy being stored per mass, which is, of course, relevant for many applications. And what you see here, so this is from Yuri Gogotsi, one of his papers, whom Kelsey will know also very well. You see here is this green area here, which I magnified here, where this is indicating the I would say the state of the art for lithium-ion batteries. You see it goes up to roughly 400 watt-hours per kilogram. And this is, as we will see in the next slide, also limiting really for this technology, mostly for materials and construction reasons. At the bottom part, you see the SiB, which is the sodium-ion battery. Sodium-ion batteries are approaching. They are at the lower end and always improved by, of course, Chinese colleagues and Chinese companies. And at the upper end, you see the SSB, which is the solid-state battery. So this is the little universe, I would say, currently of batteries. This is what's the state of the art, lithium-ion batteries. So, and we will see if we like to go beyond that, we probably have to go solid. But the lithium-ion battery is also endangered from the left side, from a lower end, by the sodium-ion battery. What at the end will happen, I think in a kind of joking way we could say, will anyhow be decided by the Chinese companies, because they currently dominate, in principle, the market. 70% of all lithium-ion batteries are being currently produced and sold alone by CATL, the biggest cell producer worldwide. And they decide whether sodium-ion batteries also will be a success, because that depends on the price of the lithium-ion batteries. So it's, I would say, quite interesting market, of course. Now, this is a paper from a good colleague, particularly from China, from Hong Li, who in a, I would say, non-battery journal, the Chinese Physics Letters, had a very nice paper where he showed, okay, as a function of the year, what is the energy, specific energy? You see here again the 400 watt-hours per kilogram, which is marked here roughly by the red line. And this limits somehow the development of current lithium-ion battery technology. And that is cells that use a graphite anode and oxide cathodes, roughly, and typical liquid electrolytes. So that's typically, I would say, a limit that can be overcome. And you see there is, of course, dots here that go higher by Jeff Dahn, for example, who's working in Halifax in Canada, closely with Tesla. And this work shows really a super high specific energy of 700 watt-hours per kilogram. And now, if you look deeper into that, you will see that can only be approached, and all these cells use lithium metal anodes already. So metal anodes, so the highest density of lithium atoms you can get in principle, and rather than graphite, where you have dilute lithium in principle, in the anode. Huh? So if you have to really pass this to achieve these energy densities, so the question is, okay, is the job being done? Now the point is, I read the paper and I also asked Hong Li, well, these cells in principle, and particularly this cell, never cycle really. They showed 3 cycles and no kinetic data. So this cell was only constructed to show you can achieve these specific energies, but they don't operate properly. I think there's still some way to go. And I'm pretty sure that at the end, these cells only operate safely, reliably, and long-term stable if you really solidify your cell. Because lithium metal operation, this is something we will see, this is a major part of my presentation. If you deposit a metal electrochemically, it tends to form dendrites, fingers, to short circuit. So that's the key issue of all the metal anodes in the batteries. And I think that's something Jeff Dahn knows very well, because in his first career, he was developing, back in the last century, he was developing lithium metal batteries, and they caught fire, and that stopped the whole development of lithium metal-based batteries. And I'm also pretty sure that we will not see lithium metal anodes or metal anodes in liquid electrolytes, but rather we always need some kind of a solid separator, a wall that really protects the cell from short circuits by batteries. Yeah. Oh, sorry. Yeah. And one could, of course, and that's something the companies, and I will have a little overview on the company issue, then, of course, try to develop. What you see here is, in principle, I would say, a little overview of what types of cells with respect to being liquid or solid you can do. So this is a cross-section, a cartoon of a cross-section of a traditional lithium-ion battery. There is the graphite here, there's an oxide here that is storing lithium, and the lithium is shuttled back and forth. You have a liquid electrolyte. The blue background is the liquid electrolyte. And roughly, you have 25% of liquid electrolyte in it. Okay, if you get rid of the liquid electrolyte and get solid, of course, the idea is already that you can also operate safely lithium metal, because the idea is that the solid electrolyte doesn't allow penetration of the lithium metal, which is the wrong assumption. I can already tell at this point, but this would be a fully all solid-state battery. But already when Toyota and other companies came up with their first solid-state batteries, there was rumors that it's very hard to get solids together 100% tight and compact. There's always porosity. If you mix 2 solids, you know that there's always lots of porosity. And the idea was that these pores are filled maybe by something liquid or jellified or so to come to almost solid-state batteries. And of course, what in China is being sold currently as solid-state batteries is not really true ceramic solid-state batteries, but is jellified liquid ion batteries. So there is, in principle, a gel polymer being used, which still contains 10 to 15% of liquid electrolyte. Whether this is really safer than the liquid cell, it's hard to know, but this is, I would say, the little universe of all the lithium-ion battery type cell concepts. And I will focus, of course, to this here, and the question whether that at the end can be operative. And in fact, there is, of course, now accepting that we have to use a lithium metal anode, then there's various cell concepts. We always have, of course, the cathode, because the cathode materials have a lower specific charge, can pack less lithium in the material. You need more, of course, a thicker cathode than the lithium anode. That's why it looks like that. They need, of course, a separator. And then they all are, I would say, differ by the type of electrolyte. So I think in the first part of, or the second part of my presentation, I will speak a bit about the electrolytes that may enable solid-state batteries before I come really to the electrolyte, to the metal anode part. At the end, I can tell you, maybe at the end, the successful cell concept will really be a hybrid cell concept where we use at least 2 different electrolytes combined. There is not a single solid electrolyte that is doing everything. There's various types, and there's not the perfect solid electrolyte. Even the liquid electrolytes we use today are not perfect. That's why today's liquid electrolytes are cocktails of a solvent, a conducting salt, and maybe 10 or more additives for certain, I would say, functions of the electrolyte. Okay, and of course, this leads, and what you see here is a time scale of we have a big research cluster in Germany on solid-state batteries, which I'm coordinating. And during these 3 years, lots of companies came up, and worldwide, big companies, startup companies, particularly in the West. In the US, there's lots of startup companies. In the East, typically it's big companies like Toyota, Samsung, or Nissan that really develop these solid-state batteries, or CATL. And it's always interesting to observe, of course, their development. What is interesting is, and which means that things are really serious, China has just last year set up a big cluster, a kind of collaborative, innovative platform, CASIP, which got roughly a bit less than $1 billion to develop solid-state batteries, because they said, okay, we overlooked true solid-state batteries, particularly sulfide type or oxide type solid-state batteries that are mostly developed in Japan and other countries. So they have now a big program, including industry, to follow up and to also, I would say, enter and conquer that field of technology. What are the scientific challenges? So I'm a scientist, not a businessman, and let's look a bit into that. What you see here is now a cartoon again of a solid-state battery, as I think many people think it should look like at the end. What you see here is then the cathode, which of course takes the biggest part, volume in the cell, where these gray spheres are then the active particles. They store the lithium. The yellow is the electrolyte, the solid electrolyte. As I said, you have to mix it, and that creates the problems with the pores and how much pore volume is there. But I can already tell you, I will not speak about cathode, but this is really very active field of research, also in our lab. Mixing solids mean you have really to design particle size distributions to really bring, let's say, plums and peas together, and to form something that really has a very, very high filling of your battery. So this is really one big field of research, which I will not discuss today. Then there's the separator. It should, of course, be as thin as possible because it's not active. Today's separators and liquid-based batteries are already thinner than 10 micron. Now, if you have a solid electrolyte that has maybe a particle size of a few micron, you can imagine how difficult that is to make a 10 micron separator out of a few particles. So getting separators is also an interesting issue, and it's a known, I would say, part of processing technology. And then we come to the anode, where, of course, hopefully lithium metal can be operated, and that will make the biggest part of my presentation, because I'm pretty sure if we do not manage to get the metal anode operating safely, reproducibly, reversible, high rate, and so on, I think the solid-state battery will probably not at least be competitive to lithium-ion batteries as such. So that I would say the future of solid-state batteries probably is, at least as a mass market product, will be decided on at the anode side. And another point is that today these solid-state batteries typically can only operate well at relatively high stack pressure. Yes, there's volume changes, there's mechanical issues, and you have to confine them, and today these pressures are still by far too high. A normal lithium-ion battery today in an EV probably has just a stack pressure of something of 1 or 2 bar, or let's say 0.1, 0.2 megapascal, and many of these cells are operated in academic labs at 100 or even 1,000 bar. And that is, of course, completely impractical. So the key issues, in fact, are today still the anode. That's my major subject. Getting good separators is another issue that's very much on processing. Of course, stable cathodes is another issue, and most of the issues are, in fact, interfaces, getting proper interfaces and let them operate. So I think, and from a fundamental issue, understanding the microstructure, charge transport, interface, and the correlations to the cell kinetics and kinetics is crucial for SSB. So if you ask me, when will there be SSBs on the market, I would say, well, I don't know really. All the forecasts always are shifted, a bit like with fusion technology. But there will be cells. Whether they will be in an EV, I can't tell you. You just have to follow Toyota's press releases, and they're shifted on and on, simply because it's not that simple, as we will see. I'm optimistic that we will see cells, but it will probably take more time, because there is some fundamental issues we have to overcome. And that, of course, attracts my interest, because as a physical chemist, I'm interested in fundamental issues, and there is enough of them. Okay, so let me briefly touch solid electrolytes. And already said, if you go for inorganic solid electrolytes, these typically are polycrystalline materials. Maybe you can have a glass, but most glasses don't have these high conductivities. The question is, if you ask, okay, how high has the conductivity to be? Now, for the separator, the conductivity, I would say, you have to approach it something like 10 to the minus 4 Siemens per centimeter, so 0.1 millisiemens per centimeter. And there's, I would say, quite a number of electrolytes that have higher conductivities, sulfides, oxides, polymers. So I think there's a good range of materials that can be used as a separator. But the critical point is the electrolyte in the electrodes, particularly in the cathode. It has to be thick to store enough charge. And if it's thick, you need a top electrolyte with a very high conductivity to have, I would say, low enough resistance to transport the ions across the electrolyte. Let's say typically 100 micron. And there, the constraint is you need at least 10 millisiemens per centimeter, roughly. And only really today, sulfide electrolytes really achieve that proper, I would say, reliably. Unfortunately, these are the most sensitive electrolytes. Polymers don't. True solid electrolyte polymers don't achieve that. Oxides just, I would say, scratch that, but not really, I would say, not good enough. Together with Wolfgang Zeyer, we devised a little graph that we felt motivated by semiconductor physics, where you often find graphs where you have a charge carrier density and the mobility of charge carriers. What you see here is lithium ion density, number density, and lithium ion mobility. Then the product, of course, times charge is the conductivity. So these are isoconductivity lines. And all these little clouds here are the different types of lithium electrolytes. We made this also a cost axis, because the more lithium ions you have, in principle, the more costly your electrolyte is. And you see here, the advantage of liquid electrolytes is they have this 10 millisiemens per centimeter at rather low charge carrier density. And if you go to solid electrolytes, you can achieve the sulfides the same high conductivity, but at the cost of at least an order of magnitude more ions in your material. So that's definitely one, I would say, of the little drawbacks of the solid state world. You need more lithium ions. As a side comment, if we switch to sodium ion technology, that is not anymore an issue, because sodium ions are so cheap. So this is definitely, so that's why going solid with sodium ion batteries has definitely also a cost advantage. Yeah, so there's, and the good thing, of course, is that inorganic chemists are restless in making better electrolytes. So today, I think there is materials for lithium-ion electrolytes that even approach 40 millisiemens per centimeter, and I know for sodium, we already have electrolytes that approach more than 100 millisiemens per centimeter. And then you have a pellet of a solid electrolyte that has only a resistance of 1 ohm or something. So this is really, so conductivity is not anymore, I would say, a barrier or a limit for solid-state batteries. We have excellent solid electrolytes. What is more an issue, in fact, is at the end, the stability, because the electrolyte, of course, is in contact with the negative electrode and the positive electrode, and in the charged state, the cathode has, in physics terms, a very, very low Fermi level. It's extremely oxidizing, and at the anode side, extremely reducing. The voltage of lithium-ion batteries, typically in a charged state, is 4.2 volt. Water is being decomposed at 1.2 volt thermodynamically. So, and that means electrolytes really are exposed to extreme chemical forces, and that's something we investigated quite also in depth, that at the anode side, then typical solid electrolytes may easily be reduced, At the cathode side, they may easily be oxidized, and you have a lot of degradation reactions. So one of the major issues in solid-state batteries is really the degradation of the electrolyte and the lifetime, which I think still is also, I would say, by and large, an unsolved issue. And we looked into that. I think I will move past that quickly, that all the different types of electrolytes all have their stability issues. What is relatively stable is one material that is a garnet-type phase, this lithium, lanthanum, zirconate, and oxide. At both sides, halides seem to be stable at the cathode side, but all the others have their stability issues, and you have to work on that. Maybe use protecting interlayers, but this is really just an independent field of research. Okay, now that brings me to the major part of my presentation, and that is really the metal anodes. So we started that a while ago, and let me introduce that by saying, okay, what is really the task? Now, if we go for a metal anode in an anode-free cell, and now here is the metal electrode, here's the cathode active material, here's the separator, here's the metal as a cartoon, and if we then in principle discharge the cell, the metal has to be dissolved, and that means an atom has to be dissolved into the electrolyte, and you create a little vacancy in the metal. You really get a vacancy in the metal, and that happens. And then, of course, this vacancy, if you like to have a stable electrode and interface, this vacancy has to be refilled. So the vacancy should be quick enough. And if it's quick enough, then, of course, you keep your stable interface, but that means the diffusion of lithium metal atoms here should be fast enough if it's to get a stable morphology. And if it's not stable enough, then you create, yeah. And if it's not, if the metal here is not fast enough, you will create, something is happening here. Yeah, you create pores. So diffusion is a very important issue here. And then upon charging, so the diffusion rate here determines really the stability of the electrode. Now, in the next step, if we have really our stable interface, then in fact, we can also nicely, hopefully, deposit metal then again at the whole interface. If you only have a few contact spots left after stripping, that is then typically the starting point for dendrites, because you have only a few, I would say, contact spots where the current is being strongly focused. You get constriction effects that are typical for many electrical contacts, and that is then typically the starting point for degradation of cells and of electrodes. Now, and that means, how does the microstructure then come into play? That is really the key subject. And that is, if you have any background in material science or even metallurgy, you will know, of course, that solids have grain boundaries and dislocations, where transport often is faster. And of course, if you have solids, crystalline solids, you may experience a lot of strain, and strain couples to transport. So the mechanics and chemical and electrochemical processes are strongly coupled. And that creates, I think, lots of the problems. And the microstructure of lithium, in fact, is crucial, but nobody really knows a lot about, there is not much known about the microstructure of alkaline metals. Everything is known about the microstructure of steel and how that determines the mechanical properties. You know that plastic properties of a metal are determined by dislocations and by the movement of dislocations. If you bend a metal wire, what happens is it's only plastic because dislocations move. If the dislocations can't move, you can't bend your metal. And because ionic crystals do not contain many dislocations, they're stiff, brittle. So it's all about, I would say, the mechanics. And as a chemist, I'm really poor in mechanics. That's why we cooperate with specialists in mechanics to better understand that all. But it was our starting point that we didn't know what is really the microstructure of a metal and what is its role for the properties of the metal anode. There was a very nice paper by Don Siegel, a theoretician from Austin, Texas, who calculated the diffusion of lithium metal. And he said what is shown here is the diffusivity of lithium in grain boundaries and in the bulk of lithium. And he calculated that the diffusion coefficient in grain boundaries is much, much faster, or the diffusion coefficients are much higher in grain boundaries. And he even calculated then, okay, what should be the ideal grain size of lithium metal to have enough grain boundaries to have fast transport in the lithium metal? Well, it's clear. If the grain boundaries are fast, you make a nanocrystalline material and you have a very high diffusion rate. And he calculated, well, it should be below 1 micron grain size. And then the question is, can we get that? Can we get lithium metal with a grain size below 1 micron? And the answer is very difficult, and at the end it doesn't make sense, because the true and the best electrode or concept we will see is, of course, something where you don't bring in any lithium originally into your cell. Okay, and this is then the story of particularly 2 brave PhD students in my lab. Nobody really had ever looked into the microstructure, into the cross-section of an alkaline metal, because they are so sensitive. In principle, you have to cut and to look at it with a suitable technique, and that was, before they did their work, not possible. So essentially what they used was a technique that is electron backscatter diffraction. Essentially, it's a technique where you use an electron microscope. You have an electron beam. The secondary electrons can be used to get all these nice pictures, of course, of the surface with the electron microscope, the morphology, but you also get information from scattering, diffraction information, essentially. And that can be used from a near-surface region to get information about the phase identity and the orientation of the grains. That is extremely difficult with the alkaline metals, because the surface always reacts with everything, and you have to be extremely careful, and they managed to have a workflow that is careful enough. And this is when we had published our first paper. There was a very nice paper coming up from Argonne National Lab with Khalil Amin and others, where they showed surface images. So what you see here is then a lithium sample, and they got just a surface image. They got their so-called Kikuchi pattern, which contains all the information on the lattice here, and then the color code simply says, okay, this is a specific for a certain orientation of your grains. What you see here, they managed, in fact, to get huge grains, and even achieve virtually single crystalline lithium films. That's possible, but they only looked to the surface of the film and only post-mortem, so it was just a foil, essentially, at this point. Okay, now, a postdoc in my lab had started earlier looking into that, and he already made electrochemical experiments and showed nicely that if you have a coarse-grained lithium and a fine-grained lithium, that in fact the electrochemical properties are indeed quite different. The fine-grained lithium, you see here much smaller grains than here, deliver much more charge for a longer time with the same current density, so more charge than the large-grained lithium. So the grain size microstructure has an influence. So we could use different foils, but the problem is, in fact, then you have really to produce them. And the question is that really stable? And of course, nobody wants really to bring lithium foils into a battery. The ideal concept is to have all the lithium in the cathode, and in the first charge step, just to produce the lithium, but not to bring lithium as a foil into the cell. It's expected this is pretty expensive to have thin lithium foils. So I think the best is to have an anode-free cell concept where all the lithium from the cathode is being used in the first step, make a metal. And then, of course, the question is, what is the microstructure of the metal that's being formed in the cell? Well, then the microstructure of the foil is irrelevant. It's more the question, what is really the microstructure of your film? And that's where Till and Till, we call them the Tillies in the group, did their work. So they were then making a little solid-state battery. They made a cross-section with a FIB, all cryo conditions. And then they were able, even operando, to look really at the lithium metal electrode principle and investigate the microstructure during operation. And what you see here is then in the color code, the lithium metal upon stripping, how it develops. And you see here pores are being created, as we saw. Big pore is being created here, and we have very huge grains. And that was sort of the starting point for getting deeper into all that. And also what we saw is that, in fact, all the pores seem to have their nucleation not at a grain boundary, but really in the grain interior. And the answer or the explanation is pretty simple. The grain boundaries are fast. And if you create a pore, I would say, at a grain boundary, the transport is so fast that it doesn't grow, probably. But if you go into the grain where the diffusion is slower, pore nucleates and can grow because the diffusion into the pore is slower. Yeah, we went then deeper into that and saw, okay, we should really look at how electrodeposited lithium really is growing and whether we can control that. So what is really the microstructure of electrodeposited lithium? Nobody had seen that, in fact, before. And this is then how it looks like for different electrolytes. If you think, okay, this is not very spectacular, but in fact, we found it extremely spectacular because it was the first time one could look into that. And you see here lithium and sodium, in fact, on different electrolytes. So this is on a garnet, this is on a Nasicon type phase, on a sulfide type phase. And the most surprising thing was we only found across all the layer 1 grain. It looks like a line of teeth, essentially. And only vertical grain boundaries. A few truncated V-shaped grains. So that was the biggest, and you see here 100 microns. So these films were already 50 micron thick. 50 micron lithium already means 10 milliamp hours per square centimeter, and for the battery specialist, that is more than you need. Typically, for a competitive lithium-ion battery, you would need to cycle maybe 20, 25 micron lithium. So this is already more than would be needed, and it's just one grain. And the question is why, and how only 1 grain? The question is it current density that is decisive? And what we found, to make that story short, is first of all, we only saw really more or less always 1 grain across all the film thickness, vertical grain boundaries. And when we let the layers grow thicker, the grains became bigger. So they changed their size with thickness of the film. And that was work by Yuri. This is, by the way, on steel deposited lithium. So what governs the microstructure really during plating? We looked a bit deeper into that, and I will make that short. At the end, we found that, in fact, the thickness is a major decisive factor for the microstructure of the film. And the reason is grain growth is so fast that, in principle, the grain size always adapts the film thickness. It's a competition between the interface energy and the grain boundary energy. If you have a thin film, the interface with the current collector and with the electrolyte determines the energy of the film. If it grows thicker, you have more and more grain boundary, relative grain boundary area, and then the grain boundary energy determines the size. And films, of course, always want to grow. Grains want to grow. And that means if there's more grain boundary area, films tend really to become more or less single crystalline at the end. And this is really, of course, quite exciting. We made a little model for that, saying, okay, there is first nucleation, grain growth, and of course, upon stripping, pores mainly are being created in the grains, not in the grain boundaries, because the grain boundaries are really fast. And that was, I would say, at that point, a first point. And then if the microstructure is determined just by the thickness and always changes with operation of the cell, we can't control it. Or is there any way to control the microstructure? Because we want to have small grains, but they always grow to big grains, which I think is a disadvantage. This was the starting point for the next things. But before I tell about that in the final part, we really proved meanwhile that, in fact, a thicker growing lithium film, always the grains get thicker due to grain growth. And so originally, let's say with the 5 milliamp hours per square centimeter lithium being grown, you have smaller grains. Well, doubling the thickness, grains get bigger. And then reducing it again, stripping, in fact, reproducibly, the grains get smaller. So it's really reversible. No? Grains grow, grains shrink. That's a function of the thickness of the lithium film because these grain boundaries really can move relatively easy due to the fast transport. Not only within the grain boundaries, of course, also across the grain boundary then. And that is, Sasha, some of you may know him, is a PhD student in my lab who also spent some time in Kelsey's lab, and it's nicely cooperating. He made a little model, like a POTS-type model, which simply calculates the microstructure of such a film, where there is only very few parameters, and the two parameters are the interface energy with the substrate and the grain boundary energy. And if you do that with a two-parameter model, you perfectly can already, I would say, get major, I would say, elements of the film growth. So for me, the story is getting quite nice because we can already model major part of the story. Okay, now, at this point, let me have a brief summary saying the microstructure, we want to have a small-grained microstructure because then we have a better electrode that can achieve higher, faster kinetics because the grain boundaries are fast. But pure lithium tends really to grow to large grains. So what shall we do? And that, of course, is what Samsung has found early on. You simply have somehow to influence your metal, let's say to dope it with something and to avoid the fast grain boundary motion. First, we thought maybe the current collector has a strong influence on microstructure, but we found, to make that short, we don't believe that the current collector has really a major influence. It will have an influence, but we don't think that it has a major influence. So you see here the microstructure of a copper current collector, and the grains are pretty huge here, and we never found really a clear-cut correlation with the current collector. But what we found is, and it's known by work by others, for example, by Jeff Sakamoto, that if you have here the electrolyte and the titanium current collector and a little gold interlayer, gold does not dissolve in lithium, that the microstructure already looks a bit different. So there is, well, you get already a few grain boundaries that are horizontal, and also if you use, if you use silver, for example, the grains tend to be smaller. It's not sensational, but there is an effect that is statistically significant. So metal interlayers introduce clear changes to the microstructure, and we get smaller grains. Columnar growth is not as pronounced, but I would say it's not yet, I would say, a sensational effect. How does it work? And with the gold, we have, meanwhile, just a paper was accepted. The gold nanoparticle at the interlayer, they really, if you grow lithium, they move into the growing lithium film. We even can identify them by the Kikuchi pattern, so they form a lithium-15 gold 4, in fact, intermetallic phase. And it's called Zener pinning, they tend to immobilize the grain boundaries, or they influence the motion of the grain boundaries and the grain growth. So, in fact, particles can change your microstructure, of course. Now, the second thing is if you go for silver, in the case of silver, silver is completely dissolving to lithium. The phase diagram is that way. Silver completely dissolves. It seems that also the dissolved silver, you have a silver interlayer, you grow your lithium film, the silver dissolves in the film and changes also the mechanical properties and the diffusion behavior of the lithium. If you strip it again, you reform again the silver film, so it reversibly works, influences then your lithium growth. It's, I would say, metallurgy in the battery. And this is something that has been really overlooked, which role metallurgy will play in a battery. Chemists are not well trained, I would say, in metallurgy. Okay, final point, and then I think I really stressed my time, is we found out during that research that the purity of our alkaline metals really is critical. But you see here, you know that this is these big salt brines in South America where lithium is being harvested. And now if you look into what is the quality of today's lithium, if you buy lithium metal, it's pretty dirty. You often will find impurities of 1 or even 2% of what? Yeah, mostly alkaline metals, sodium, for example. If you look into the phase diagram of lithium-sodium, you'll find lithium and sodium are virtually immiscible. But you will find impurity contents of 1 or 2%. That means there is sodium particles in your lithium. And very little sodium is really being dissolved in the lithium. And depending on your supplier, you have different qualities of lithium. And we found, by the way, that, in fact, this is really critical, because if you take different qualities of lithium and strip it, the impurities, of course, don't dissolve in the solid electrolyte. Because the solid electrolyte, that is very specific. Solid electrolytes are highly specific for the mobility of one charge carrier. The sodium simply does not enter into the solid electrolyte, so it remains at the interface and increases the resistance of the interface. So with a very pure lithium, and this red here with the high capacity is ultra clean lithium that was beforehand electrodeposited. So that is anode-free, so to say. Lithium is a very high capacity, whereas all the commercial foils have relatively low capacities, because lots of sodium, in fact, really is accumulating during stripping at the interface, unwanted, of course. So there's something very important, and now this is what we're exploring. And impedance studies, and I would say very detailed impedance studies, we really found that in these impedance studies, really impurities have their own signature. You can really see them even in the electric characterization. Okay, I think my time is over, so I will skip the sodium subject, saying that with sodium everything is better, and and Anna will be happy about that. Now, sodium has a lower melting point and has a higher diffusivity, so that's why you can easier grow thicker sodium films. That makes sodium, of course, quite interesting. This is needed because 1 milliamp hour per square centimeter charge in the case of sodium makes roughly 10 micron length change, where it's only 5 micron for lithium. Okay, now I'm a chemist, and it's very important, of course, to go down the row, right, in the periodic table. We even managed, meanwhile, to look into potassium. So I have a very brave PhD student, Max, who managed to grow potassium on potassium beta alumina. There you will have, with 1 milliamp per square centimeter charge, 20 micron thickness, and you get very nice Kikuchi pattern. The electron density is higher, so everything works reasonably well, and you get almost only 1 grain. So it's even single crystalline growth of potassium, because it's even faster. Diffusivity is extremely fast within potassium. Okay, now just one final bit. There's one more little thing, and that is the pore growth. Nobody knows how do the pores nucleate. And just a few weeks ago, we submitted a paper. We thought, okay, the only way really one of the potential ways to determine pore growth is simply to measure the length change of an anode, very, I would say, sensitively. And if you have a metal piece, and if it really is being dissolved layer by layer, you get, of course, a continuous thickness change. If pores are being created, well, you don't see that in the outer length of your electrode, right? So making a dilatometric experiment with a nanometer resolution will allow you to get that information. So I have an engineer in my group who was very good in setting up this dilatometric experiment, and we managed, in fact, to measure that. And what you see here is now an experiment in this busy slide. Again, this is the charge we take out of the lithium metal, and this is the pore volume that is being created. And you see here the red curves are with 2 different charge current densities. In fact, from the very beginning, in fact, we create pore volume. And that means that you can't avoid, and this is really zero pressure experiment, only essentially 0.6 bar pressure. From the very beginning, pores are being created in the lithium, which of course is a critical issue. And we came up with a model saying, well, you always have from the very beginning on nucleation of pores by injected vacancies, and then there's different periods of grain growth, partial collapse, and so on. That is a complicated chemomechanical issue that currently can only be overcome by high stack pressure. That is too high for practice. And this is, of course, the challenge, I think, that has to be overcome. Okay, now, take-home message at this point is simply the lithium-ion batteries are moving targets. They get better and better and better, but they will not exceed the 400 watt-hours per kilogram. You can only overcome that with lithium metal anodes, but their, I would say, safe operation is today not secured. And I would say it's a big bet whether that will operate. We still have fundamental issues to be solved, I think. That is, I would say, by really tackling metallurgy of lithium metal and sodium metal properly. Then we can have true high energy cells. I'm pretty sure we can also high power cells if that is being solved. And with that, I thank, of course, our funding agencies, particularly, of course, the PhD students and postdocs who do really excellent work. And, of course, I thank you for your kind attention. Thank you.
Okay, you did quite well on time. So we have time for questions. Nicole?
Yeah. Yeah. Okay. Yeah. This is, in fact, as you saw here, this is unpublished. We got only, I think, so far 2 of these images. So this is really just spoilering into the subject. I would say we get the impression that the grains are thicker than in the other cases, but we don't have any statistical information yet. Take it as a first. Take it as we are able to get potassium information, but we don't. I can't tell you really reliably any quantitative information on that. Yeah. But we are looking now deeper into that.
Lynn?
Thank you, very nice talk. I have a question regarding the grain size of this deposit lithium. So you mentioned that as you deposit more, sorry, thank you. So as you deposit more lithium onto a current collector, the grains are tending to grow larger. So I think that's associated with like larger grains absorb smaller ones. If that's the case, say the grains are experiencing some like reorientation, like recombination, do you expect any like local stress, like stress distribution change? And will this affect any electrochemical performances?
Yes. Yes, for sure. We see, of course, grains disappear. We even see rotation of grains. And I think, no, that's something, again, this is not my field of research originally, this kind of, I would say, metallurgy. That's why we connected with really metallurgists and specialists for these, I would say, metal properties and grain growth to understand better what is really growing on. I think we are just at the tip of the iceberg concerning that. We just learned how to image these things, and we are happy to know that in Kelsey's lab, she's using complementary techniques, so diffraction techniques to get information on the microstructure. So I think, I hope that we can compare that at the end. I would say this is maybe, I think, just the beginning of the story. Yeah.
Thank you.
Ian?
Thanks for a really interesting talk. So I'm sorry to drag you back onto the iceberg of metallurgy again, but just to probe a little bit about the anisotropy of these grains that are forming and whether that affects, I guess, lithium mobility to the surface or the interface and the conductivity as a function of orientation. Do you find that there's preferred orientations that give rise to
this? Is
that controllable somehow?
Yeah, this is something we already discussed. I think there is so far really only very small number of works. There's one from Shirley Meng. They say, okay, we see preferential orientation, but they have a rather, so far, very, I would say, small statistics, only a few grains. I think then it's difficult to make really proper statistics. We have, meanwhile, managed to make really millimeter-wide images where we have 150 grains analyzed. I would say we don't see currently a too strong, I would say, preferential growth. I would not exclude it anyhow. But it seems that particularly if you use interlayers, that helps more preferential orientation. But I think this is too early really to conclude on that. But this is, of course, an interesting, very important question and point. I should say that what we also see in the EBSD analysis, there is also can analyze, of course, also how, what is really the deviation from the perfect orientation and so on. And we see that also the orientations, somehow there's some ripening also with time. So there's lots of details I excluded right now. Yeah.
Oh, and then Tom. Or you can go.
Hey, my name's Tom Lydon, class 77. I have a very practical question for you, but I'm in the commercial solar development business, and so I'm rooting for you. Solar and storage. I'm rooting for you.
Oh.
He's a solar guy.
Lower the cost of battery storage.
Yeah.
But I'm a fellow here at the Andlinger Center to help students look at careers in clean tech, and I was wondering, in what you do, what kind of career opportunities would be here?
Oh, well, I think, of course, that I'm pretty sure that we go more and more electrified. I have my own photovoltaics with a battery, which has to be coupled. And well, even if we at the end will have fusion reactors, we will use, of course, lots of batteries. So I would say, in particular in the future, I think the battery market, the EV market, of course, is a big market that will be covered by big companies. But I think at the end, there will be such a high demand for high power, rather specific batteries for exoskeletons, for high power tools. For that, we need, of course, very specific, very high power batteries that really have, I would say, a very specific profile of properties. And we see it in the US that there's, of course, lots of startups going into different directions. So career path, I would say, my students, in fact, most of them end up currently at OEMs, but also quite a number of them in smaller companies. I think I didn't see so far an unemployed electrochemist. Really, honestly, electrochemistry is flourishing.
Good news.
You can't make anything wrong going into electrochemistry, really.
Hi, Jürgen. Sorry. Hi, Jürgen. Srinka here. Thank you so much for the talk. Very amazing. Also, thank you for that comment. I think as a graduate student who will be graduating in a couple of years, I feel very reassured by your prediction. Hopefully the market stays that way.
Yeah, maybe I should say what my comment was from the German current.
Yes, yeah. Yeah, we'll see about that in the future. So yeah, I think my first question is regarding the interlayer that you talked about. I wonder, what do you think about the chemomechanics contribution of the interlayer? Because you mentioned that it's kind of reinforcing this grain boundary, right? That sounds more like a mechanics effect. But do you think the interlayer also maybe alter the SCI of the lithium metal somehow as well? Maybe it stabilizes it, but
yeah. Let me answer with a paper, not from us, but from Matt McDowell in Georgia Tech. So they have a nice paper probably coming out soon. Which is already available at ChemArchive, anyhow, where they show that I would say not too thin, sodium interlayer for lithium electrodes very much improve the kinetics, and they explain it and what they do is they prepare lithium electrodes, lithium foil, with a lot of sodium inside, which is forming particles, so it's really it has really sodium particles because, as I told, the lithium doesn't dissolve sodium. And then upon stripping, seems to form a thick sodium layer, and sodium is, of course, softer than lithium. It seems that this soft interlayer helps keeping contact and avoid forming pores. Still some questions. We had a meeting with Matt because we tell that sodium is an issue. It degrades the interface. They say, okay, if you have a thick sodium layer, it's good. I would say, so there's some questions. I can't tell you, but this is an example that, in fact, the layers may, of course, improve the chemomechanics. And originally, I thought that, for example, just a polymer interlayer could be good. So far, I think we didn't really succeed to get a good one, but yeah. Of course, when it comes to cost, the simpler the system, the better. The more components, the more expensive. So we have to fight against let's say, I think the kilowatt hour LFP cells from China are already below $50 per kilo. And this is maybe not the end. So at the end, really, I'm unhappy with that, but my colleagues in industry say cost.
Well, thank you so much. So the kind of second question is more like maybe just generic for the battery industry. Because you mentioned a little bit in the beginning, right? Like China, like CATL dominates the battery market by like 60-70%. And whereas in like Europe or America, we see a lot of big companies, such as in Europe, Northvolt recently just went bankrupt. And, news like that, and also in the US where, yeah. So what do you think about the future battery market is like for like European and American sector versus like Asia?
I think that's probably more a topic for after dinner beer, or beer, several beers. But let me try to give a short answer to that. Of course, what we see is, honestly, that we run into a bipolar world, where currently, because China simply went much earlier professional into the battery market, so that they learned really to tackle all the production issues. I have a friend in industry years ago already told me, give me a good chemistry and 3-4 years, and then you will have a good cell. So processing and production engineering is extremely important, which we as chemists always underestimate. And what I learned is that I think the advantage of the Chinese producers is simply that they have of course, an advantage. They went into it early and they learned simply to produce properly with a low scrap rate. If we set up, and that was a problem of Northvolt, if we set up a gigafactory now, after 1 year we have 30% scrap rate. And this is, of course, that doesn't work. Let's shoot up your cost. So, and the point is, I think if we want to compete, unfortunately, we have to accept that we have to spend billions to keep up and to get the same level of experience. If we don't do that, we have to buy Chinese cells. Quite simple. That's true for the US and for Japan. Maybe the US can build a big wall around itself. Europe cannot. So, yeah, Europe cannot, and I think we will not. So we try to fight. And of course, there's victims along the fight, I would say. Yeah.
Okay, for sake of time, we'll end there. Thank you.